Okay, so hello there folks, and welcome to the channel EMF Informer, the first channel of its kind in the UK, looking into the effects and the science, safety of electromagnetic fields, or EMFs, in various frequencies from low through to radio and right up to microwave frequencies. So this is a channel dedicated to informing folks who are non-electrical engineers and not part of the telecommunications industry about the ways that devices work, transmit electromagnetic waves in the various frequencies, and what the health and safety implications are. We'll be dispelling some myths along the way, covering some of the latest research and providing you with tests from our own lab setup. So this is a channel where everything is intended to be backed up by solid maths and science. We inform you so you can draw your own informed conclusions in the realm of EMF. So without further ado, let's look at today's topic, which is Elon Musk's Starlink satellites. So they've gained a lot of press, and there's also been many concerns raised. I've had several people asking me how this satellite cluster works and if there may be health issues from the way the satellites are transmitting. So for those folks in a hurry, I'll provide a conclusion right away, and then the rest of this video will be backing up that conclusion and providing the detailed background information and the science that led up to that conclusion. So looking at the currently set levels, well, the safety levels, by even the most stringent of the international standards on safety levels for RF and EMF, such as IGNIR and the Bio Initiative, also the European Parliament study from 2016, I can say there simply is not a high enough energy level in the beams transmitted from Starlink satellites to exceed any of the safety levels of these safety levels in the normal operation of these satellites. The signal, when it actually reaches the Earth, is around 1 millivolt per meter. So even if several satellites could somehow beam onto the exact same spot at once, the EMF level would be just a couple of millivolts. This is a tiny level, and as we will show, it is almost undetectable. So certainly these new satellite constellations are adding to the overall electrosmog that we live in, and that can't be a good thing. But compared to all the mobile phone and Wi-Fi transmitters around us, the EMF exposure caused by Elon's satellites is currently extremely small. Okay, so without further ado, let's move on to the first slide. I've laid out a set of points here that we can just look at. So at present we have just over 2,000 satellites orbiting. Each satellite actually has several transmitters on it, one of which is to backhaul the data. Now this transmitter connects with an actual Earth station, of which there are about 8 around the world, and these have a massive satellite dish on the ground, and each satellite can connect to that to backhaul the data it's gathered from home users and subscribers around the world, and it transmits that to the ground station. Each satellite can also communicate with each other via another transmitter, which is actually a laser beam. That does not affect us at all, so we won't cover that. Each satellite is designed to cover an area on the planet's surface of 956 square kilometers. And the satellites have been assigned a frequency band from 10.7 gigahertz to 14.5 gigahertz. Are Starlink satellites a cause for concern? So the points that we have are obviously exposure to people who are electrosensitive, who may be more affected than usual people. Obviously, the satellites create a lot more possibility for space debris. They do also affect astronomy. There have been great concerns by various astronomical labs about the problem the satellites are causing for those with telescopes. And also they have a higher carbon footprint. These are the main concerns. Aside from these, though, satellites do not, as I have said, have a major concern for the sheer level of EMFs that hit the planet's surface. If we look at this little calculation here, at an average of 600 kilometers above us, the satellite's signal is actually losing power to 103 decibels as a minimum by the time it gets to us here. Now, for those who don't understand the system of decibels, that is equivalent to a loss in signal strength of nearly 20 billion times. So a signal, for example, which was originally 3 watts in power from the satellite in space, by the time it reaches our receiver here, is in the order of about 1 nanowatt, which is a very tiny signal. Do look that up. Okay, so as we can see, each satellite does beam down. Each beam covers an area on the planet as the satellites are moving across. They travel at an enormous speed. So each satellite is going through each of these little zones of coverage for a matter of minutes. Okay, so let's look closer at these cells. That each satellite covers many cells as it moves over. So if we look here at Wales and the southwest of England, a typical satellite would cover all of these cells, each of which is about 25 kilometers square. Sorry, 25 kilometers in width. Obviously, only the cells which actually have active subscribers in them would be serviced. So at the present time, we can see just the green cells here actually have active subscribers. And so anywhere where you can see the red cells would not receive any beams or coverage from any of the satellites, because why would they waste their power on servicing an area where there's nobody to actually receive the signal? So each satellite actually can transmit up to 8 beams at once. So simultaneously, it could be servicing 8 of these green cells. As we can see, there is a limit on the number of subscribers, because at present Elon Musk doesn't have enough satellites up there to be able to provide enough bandwidth to more than 1 million people around the world. At present, there is actually only 250,000 subscribers. Okay, so let's look further at these cells. As you can see, each beam from the satellite transmitter is directed, and there can be 4 or 8 beams at once, each covering a different area and transmitting to a different subscriber. Later on, I shall show you a picture of a typical satellite dish, which each subscriber has here on the ground next to your house or on your roof. The dish actually has 1,260 very small antennas on it. Each antenna is slightly smaller than the antenna in a mobile phone. However, all of these antennas work together to steer the beam exactly to the satellite. So this is a very new way of transmitting. Traditionally, mobile phones, for example, transmit in a 360-degree area all at once. So the beam has to go out a bit like a light bulb in every direction. However, these satellite dishes have a narrow 3-degree beam, and all 1,260 of these small antennas point in the same direction and steer the signal on this 3-degree beam directly at where the satellite is, which the antenna needs to know, and it's tracking these satellites. As you can see, there's about 240 megahertz of bandwidth for the techie people. And the modulation used is very similar to that used by mobile phones, or especially that which will be used by the 5G mobile phone masts. Okay, for the maths lovers, I have a slide here giving you the actual maths behind my calculations for the signal strength when it actually arrives here at the receiving dish from the satellite in space. All of the calculations are there, as you can see, and the results, we're looking at something around minus 68 decibels or decibel milliwatts when it actually arrives at the receiving dish, which, taking into account the gain of the dishes, which is about 33 decibels, we can calculate that the actual received power is less than 1 millivolt per meter, which, as I've said, is a tiny amount, especially compared with mobile phones. So if we look at a picture here, you would need to literally be sitting out in space with your laptop and the satellite dish attached to your chair to be able to receive any sort of strong signal from these satellites, which is why you need such a large dish to receive the signal. Another slide with more calculations, this time showing the more likely power received, because on the previous slide that was the most optimal variant for the power received. But here, as we can see, when we take into account the actual loss of the signal through the atmosphere, which does attenuate the signal considerably, especially if there is bad weather, rain, mist, snow, anything like that will cause the signal to be massively less, which is why people find that their bandwidth is reduced when connecting to the Starlink satellites in poor weather. So taking into account more usual conditions, we can see that the actual received power would be about minus 76 decibels, which is 0.28 millivolts per meter, which is a very tiny signal and is basically impossible to pick up without special equipment and special amplifiers. Talking of which, I have used one of the spectrum analyzers that we have here in our lab. It is a top-of-the-range industry standard spectrum analyzer with a very sensitive Aeronia antenna, and as you can see in my part of Wales, pointing up at the Starlink satellites at the exact frequency that one would expect to receive some signal from them, we can see on the screenshots here, it is just pure noise. There is absolutely no signal whatsoever above minus 85 decibels. If the satellites were transmitting, we would expect to receive a slightly higher signal than that. Clearly, I'm not in a cell here which is receiving coverage, and I would go on to say that in most parts of Britain and the world, we would see the same screen on the spectrum analyzer as we see here. A mobile phone, for example, would be many orders of magnitude higher than what we're looking at here. Here we can see a few pictures of the Starlink dish, which is sent out to subscribers who sign up to Elon Musk's deal. Each dish is rated at up to 3 watts of transmission power, which is roughly the same as a powerful walkie-talkie, such as those used by the police. However, the dish does transmit that power in a very narrow 3-degree beam straight up into the sky. So it works very different from traditional antennas that we are accustomed to. The gain of the antenna is very high, nearly 34 decibels, which it needs to be to actually get that tiny signal, which is usually around 1 watt, maybe 2 watts, to reach the satellite nearly 600 kilometers out in space at a very high frequency, as we can see there. The field of view of the satellite is about 100 degrees across the horizon, so it can actually track the satellite as it appears over the horizon. Like the sun, it travels across the sky and sets on the other side of the horizon, and these dishes actually have a little motor in them, and they actually slowly move and track the satellite. If we actually calculate the power from these satellite dishes using the EIRP, which is the equivalent radiating power of a 360-degree antenna, a theoretical one, i.e. if we had an antenna like a light bulb that needed to transmit in every direction rather than just in a tiny 3-degree beam, that antenna would need to have a power of 6.5 kilowatts to achieve the same thing. So don't be confused. These antennas are not transmitting at that power. They are transmitting at a couple of watts, but they can do that because it is a very thin beam and it's not transmitting in 360 degrees. So let's look at some conclusions, some comparatives here. As I've said before, these satellite transmitters and the satellites have very tiny signal strengths and comparatively low transmission powers as well, especially compared to mobile phone masts. It is all about distance. So at typical distances that you would be from these devices, we can see that many of the common devices in our everyday lives are orders of magnitude higher than a satellite system, which we can see is around 0.2, maybe up to 1 millivolt per meter. So exposure in a typical home is going to be 5,000 times higher in EMF levels than you would receive from these Starlink satellites. So, as I say to folks very often who ask me, in the world of RF, radio frequencies, EMF, transmissions, it's all about location, location, location. This makes the biggest difference to signal strength. It doesn't matter if you've got a satellite, a mast, a radar, an aeroplane, a mobile phone. If it's a long way away, it's going to be a very tiny signal strength, very low exposure to EMF. And if it's close to you, it's going to be very high. For example, Bluetooth headphones have an extremely tiny output power, but because they are in your ear, they're going to be thousands of times higher than the signal strength you would get from a mobile phone tower or a satellite, simply because they are so close to you. So I put a few examples here of the transmit power, for example, 200 milliwatts, which is typical for a phone. I've also put 20,000 milliwatts, which is typical for the tower here, and shown what sort of strengths, what sort of exposure you would expect on your body from these. So finally, let's look at possible misconceptions that I read about on the internet. I have been in this industry for some years now. I have spent many years working on this, researching in this field, and I hope that I can give some expert enlightenment on some of these common misconceptions. So let's look. We have here 5 of them. The first one: people report that the Starlink satellites give out 4.5 million watts of power. This is not true. This is actually a misconception and would be impossible, since the solar panels on these satellites are actually only capable of creating around 4, maybe 5 kilowatts of power at the most. So this figure here is people confusing, again, this EIRP, which is equivalent isotropic radiated power, i.e. what a 360-degree antenna would theoretically need to put out in power to achieve the same results as the satellite beam, which is only 3 degrees. Okay, the second one. Elon Musk's satellites are not a part of the 5G rollout and actually have nothing to do with 5G apart from using the same mathematical modulation scheme for encoding the data into the signals. It was some sort of coincidence that actually his satellites were put into space at the same time as the telecoms networks here in the UK actually rolled out the first 5G masts in the big cities. However, they are not part of the same system and are not very similar. The frequencies are very different. 5G frequencies are 3 to 4 gigahertz. The Starlink satellites are around 11, 12 gigahertz. So a completely different system. The last one, some particularly electro-hypersensitive people have asked me, will these satellites disturb my sleep? Because as a lot of people know, Wi-Fi and mobile phones do disturb people's sleep at night if they're in the room with you. However, I can confirm that the signal from the satellites is so tiny, around 0.3 millivolts, by the time it gets through a roof, which is 15 decibels of attenuation, that reduces the signal by another 32 times. It would be less than a nanovolt. It would be negligible in comparison to what you would receive from typical mobile phones, typical electrosmog levels. The Starlink satellite dish itself, is it dangerous? I could certainly say that at less than 40 meters proximity, if you were actually high enough that it was the beam was actually touching you, it would be hazardous over time. But a 3-degree beam going straight into the sky is very unlikely to be dangerous. The only worry might be is if your house was high on a steep hill and someone in a camper van was down below you using one of these dishes. Perhaps it might be able to get to your house, but it's very unlikely. Regarding electrosmog, with all the 4G masts, with 5G and with the satellites, it's all cumulative. So certainly these Starlink satellites are adding to the electrosmog that we live in, which isn't great for our health, but the satellites themselves are a very tiny part of that compared to the mobile phone masts and the mobile phones themselves. Okay, so let's take a quick look finally at one of the dishes. And this is very similar to the dish that's actually on the satellites themselves. As you can see, it's about 0.5 meter wide. And if you look, you can see each one of these little circles is an antenna. So 1,260, something like that, of these antennas. They're all fixed and they all work together, putting out a tiny signal, but the signals use constructive interference to create a narrow beam. Okay, any questions, comments, please do write below. Obviously, please do check my channel. Yes, so finally, to conclude, please do check the other videos in the channel as they appear. Please subscribe, and I do hope this was useful for everyone. Okay, until next time, goodbye.